Hello, welcome to our Wednesdays at NICO seminar. Today, I have the pleasure of introducing our speaker for this week, Cheng. He is visiting us from the University of Minnesota, but he's got a long background of being at many other impressive universities. His bachelor's is from Peking University, one of the top universities in China. PhD from the University of Chicago, down the road here with Sid Nagel, and he did a postdoc at Cornell. Didn't quite overlap with me there with Itai Cohen. He's worked on a huge range of really interesting things. All of it, I would say, fits into the category of complex systems, something that we at NICO are obviously very interested in. But also maybe within the physics of soft matter, he's looked at granular mechanics, shear thickening and shear thinning, nonlinear fluids, raindrops, or at least in analogs to raindrops. He's an experimentalist, which I respect because I have not had great luck when I have tried experiments myself. Experiments, if you don't know, on average, experimental PhDs take about a year or more longer than theoretical PhDs. So you got to be good to do an experimental PhD. Xiang has also won an incredible number of impressive awards. He was he won the NSF Career Award for early faculty, very competitive. He won a Packard Fellowship, won a DARPA Young Faculty Award, and it goes on. I'll just give one or two more highlights. He also earned a Metzner Early Career Award later than these others. And he is now a chaired professor at Minnesota, McKnight Land Grant Professorship, holds the McKnight Land Grant Professorship. So I'm excited to have him here. I'm excited to learn about his newer work on swimming, on swimmers, and how that connects to a lot of the work that's going on at Northwestern on this topic, including by Michelle Gervin, one of the NICO core faculty, who unfortunately has a conflict, so she couldn't be here. But she might be watching a recording later. So let's all welcome Xiang and see what he has to say. Thanks.
Oh, thank you for the warm introduction. It's always good to come back to Chicago. That's what they say, that I got my degree in Chicago. So I really love the city. So. Our group study wide range of fluid mechanics problem, from raindrop all the way to granular flow or suspension flows. So I'm going to give a talk on drop impact tomorrow in physics, another seminar. But today I'm going to mainly focus on our study on micro swimmers. So before I get started, I'd like to mainly say who really did the work. I just gave the message, but people do the work. Mainly my two students, Xiang and Greg, they are graduate students in my group. And we have collaborator Xin Liang, and they are theorists helping us develop some theory. And Suk from University of Cincinnati, she did a lot of simulation for us. I don't know the background of the audience here. Let me just give a very sort of a brief introduction about why we're interested in how micro swimmers swim. So micro swimmers swim at really small scale, and their speed is not that high. So if you calculate this very important number called Reynolds number is typically on order of 10 to the -6 all the way to 10 to the -2. So it's a very small Reynolds number. At this really small Reynolds number scale, essentially viscous force dominant everything. There's no inertia in that environment, right? So even though we're talking about swimming, the swimming of micro swimmer is very different from the swimming we see or we experience. Although they're very important, right? Everyone's coming from there. So it's really important to understand how they swim. Mathematically, if you don't have inertia, essentially this nonlinear term and the derivative with time term goes away in Navier-Stokes equation. Essentially, you get an equation with no explicit time dependence. That means that if your boundary condition is reversible, everything is perfectly reversible. This is a very famous video by J.I. Taylor back to 1960s, where they show you this really dramatic effect when Reynolds number go to 0. Some of you probably already see this, but I like to play this video again.
Here are two concentric cylinders. Can be moved by turning the inner cylinder with this handle. The annulus between them is filled with glycerine. Into this space, I introduce some dye, which stays put owing to the high viscosity of the glycerine. Note its position before I start turning it. I now turn it 4 times. Pushing the handle clockwise. The dye seems to mix as a drop of milk mixes when it is stirred into a cup of tea. Now I reverse the direction. And after turning exactly 4 turns, the dyed area reappears in its original position, with a little fuzziness due to molecular diffusion.
So, right, everything is perfectly reversible. There's really no much of mixing happens because Reynolds number is so slow. There's really no inertia effect. If you're applying this into the world of Michael Swimmer, there's a famous theory by Purcell who got Nobel Prize for NMR, but in his later years, he studied Michael Swimmer. He has this very famous paper called Life at Low Reynolds Number. If you haven't read that yet, please read it. It's a very, very interesting article. In this article, he proposes what they call scallop theorem. Because it's perfect reversible of the fluid, for scallop in low Reynolds number world, it cannot move anywhere. Simply because if you can open up or close, it would just go back into the same location. In high Reynolds number, the reason why scallop can move is because it can open up its shell very, very slow and close very fast because inertia will push the scallop forward. Low Reynolds number, no matter how fast you open, how slow you close, you will exactly go back to the same location. So if you have a time symmetric reciprocal motion in low Reynolds number world, you cannot swim. So any of the micro swimmer cannot use that to move around. I cannot find the example of scallop, but I found this very interesting paper using this idea. This is a fish lava. Reynolds number is not that slow, but it's still low enough. You can see the flow is really reversible. This lava tried to get this food particle into his mouth, but then when it's closed, it just spill out because everything is reversible. And look at this title here. They claim that the reason why 99.9% of fish larvae die in the first week after they hatch is because they cannot get food into their mouth. This is a nature way to select larger larvae that has a little bit higher low Reynolds number, so you can sometimes get food particle into the mouth. So very cool way to select larger larvae in nature. Why do you believe that zero? Now this fluid mechanics is very clear. Okay, so this is the word of low Reynolds number. And now I'm going to the outline of my talk. I'm going to talk about swimmer at this low Reynolds number world. So 2 stories. One story is about bacteria. Another story is about the algae. This is a prokaryotic, and this is a eukaryotic cell. Okay, so first, swimming of bacteria, E. coli. Okay, this is probably the most well-studied organism on Earth. How E. coli swim, how E. coli can overcome this Purcell theorem to move forward. The way E. coli move around is they form a bundle of helix. So the general idea is that it grow randomly multiple helical filament on their surface, and each of the filaments is driven by a small motor. This motor only 50 nanometer in scale, can rotate in both directions. If all the motor rotate in the same direction, if you look from behind, rotate counterclockwise, the bundle will come together. All the filament will come together from a single bundle, and the rotational bundle will push the body forward in one direction. The bundle can, as I said, the motor can rotate in both directions. When one of the motor rotates in another direction, the bundle cannot stay there anymore. What happens is that the whole bundle just open up. Then the body will randomly turn into another direction. So you got what they call run and tumble motion. Essentially, the idea is that when all the motor rotate the same direction, you have a single bundle will push bacteria forward. Then once a while, on order 1 second, one motor rotate in another direction, the bundle just open up and the body randomly turn. And then on order of 0.1 second, all the filament come together again because the motor now rotating in the same direction. You form a bundle again and moving again. So you get this what they call run and tumble motion. The reason why they do that is because they can couple how frequent they turn their motor to the chemical clue in the environment. So this gives them the chemotactic behavior. They can always swim to the direction where there's food, swimming away from the direction where there's toxin in the environment. One feature that's very important for my talk later is that you can imagine if all the filament grow randomly on the surface, when the filament forming a bundle it's going to be very rarely that the bundle line up with the body, like what I show you here. Sorry, wrong direction. Like what I show you here. In this case, I put all the filaments symmetrically on the body. Of course, when from bundle, the bundle axis will line up with the body axis. But this is a very rare event. Most likely, the bundle will form some angle, I call that alpha here, with the major axis of the body. When that happens, because you're pushing the body in this direction, body will slide in this direction, your trajectory actually is not a straight line, it's rather a helix, okay? And then if you do optical microscopy, this helical trajectory in 3D become wobble in 2D. That's what I'm showing here. Typically, you don't see the bundle because the bundle is really small. It's on order of 20 nanometer in thickness. In optical microscopy, you only see the body. You can see this guy really wobble back and forth, simply because it's actually doing 3D helical trajectory. And this guy here wobbles so badly, it's almost like gyrating. You see that guy? It's almost doing this. That's because the angle here is close to 90 degrees. So when that happens, you get a very slow speed, but you wobble a lot. This is one feature people know, but I'm going to use this feature later on in my talk. So the study I'm going to show you here is really inspired by a research by my senior colleague in my department, Ed Kastler. He retired right before pandemic. 2003, he is interested in this question: will humans swim faster or slower in syrup? Okay, syrup is about 2-3 times more viscous than water. And he decided to run experiment. He got a professional swimmer athlete from University of Minnesota, fill the whole swimming pool with this glucagon solution. Very hard experiment. He bought this dry powder of glucagon, has to borrow a big pump to mixing the powder in the swimming pool. And everything becomes so slippery that everyone falls on the ground. Also, because you have human subject in this experiment, you have to apply all different permits to do the experiment. The hardest permit, so he tell me, is to convince the city of Minneapolis that after he run experiment, he can dump the whole swimming pool of syrup into the city drain sink without causing any environmental issue. Anyway, it's worth it. He got the Ego Nobel Prize next year in 2005 because of this work. Okay, so what do you think? Will people swim faster or slower in syrup? It's just a Newtonian in the speed that we beating in water. Lower or higher or same? Who think it's going to be slower? Yeah, I think most people think it's slower, right? Because you feel more viscous drag. Here's the result. It doesn't matter. So no matter whether you do butterfly, backstroke, whatever the way that you choose, the speed is essentially the same as in water, normalized to 1. The argument is that at this scale, this viscosity scale, the viscous drag you feel, the actual viscous drag you feel, is balance out the inertia that you gain by pushing on something more viscous. And the end result, you get some similar speed. But I want to remind you, at the beginning of the talk, Reynolds number here, 10 to the 6, inertia is very important. And someone read an article in Nature saying that had Ed Kastler done his experiment on swimming bacteria instead of human, he would have recorded much slower time in syrup than in water. The idea is that when you have something like 10 to negative 6, there's no inertia effect. The only thing you feel is the drag, then you should have a lower speed. The idea is actually pretty straightforward, right? If you have, this is a typical motor output of a bacterial motor. So the torque output of motor is a constant. If you have your load line, when you're increasing the load, you have to rotate slower, right? Go, yes.
Use the mic so that people online can hear. Do you know, so that it's more complicated than just swimming in this experiment because there's the interaction of the person with the surface and the time they spend in the air.
Yep.
You know, if he gave them like time to learn how to swim in the syrup, or
they try several times and then they just time the swimmer there. Yeah, but I do get a question about what type of cell you have. Butterfly, you may have you most of your body outside the water for longer time, but the result is very similar idea. Okay. So back to here, I give you an analogy here. It's like you have constant torque on your battle of bicycle, but now you're going up hills. You get more load, then you have to battle slower. That's give you slower speed. That's essentially the idea for bacteria. But apparently, whoever wrote this article here, he didn't check the literature. Back to 60s and 70s last century, people already run an experiment. They put in some polymer in water, make the viscosity of water higher, and they put all different type of flagellar bacteria, including E. coli, the organism we talk about here. They found that when they increasing the concentration of polymer or increasing viscosity in this direction, So they plot in terms of fluidity, which is 1 over viscosity. In this direction, increasing viscosity. You can see all different type of bacteria, their speed goes up until you put a lot of polymer in, start to go down. So this is really mind-boggling, right? Bacteria is not even like human that just keep the same speed. Actually, they speed a little bit faster than before. Down until you put so much polymer there, they slow down. So why that? And of course, there are many, many work after that. So I only list a subset of the research. This is more recent work. They show that when increasing viscosity of fluid, viscosity go up, increasing viscosity of fluid, velocity of a swimmer goes up. So this is apparently very important. That's why people still focus on this, because in nature, very rarely bacteria swim in water. They always swim in some environment where you have proteins, DNA, so all different macromolecules and colloid particles. So you have some non-Newtonian complex fluid structure, and you need to understand how they live in their natural habitat. And of course, over 70 years, there must be some explanation why that happens. I give you some major theory why this happens. The first one is from Howard Berg. He's really giant in the field of locomotion. He passed away last year or 2 years ago. So his idea, right after that paper in 1970s, his idea is that when you put a polymer into a solution, polymers start to form gel network. And the bacteria really swim through the pores formed by this gel network. And this is apparently wrong, because we know that even you have a polymer forming gel network, the whole of the polymer network should be on order of a radial gyrational polymer coil, which is on order of a tenth of nanometer. Bacteria is 1 micron, it's too big for the whole. So this certainly doesn't work, but because of the influence of Berg, this is still the most cited mechanism in biomedical literature. So if you go there, you check why bacteria swim faster there, they're always citing this Berg, saying this reason. Someone understand the polymer physics better, they propose some new idea recently. So the another idea is that, remember I tell you that bacteria rotating their flagella, and the body will rotate in the other direction to balance the torque. The flagella actually rotate 120 hertz over the scale of 20 nanometer. 120 hertz meaning 120 times per second. I cannot do that with my finger. Okay, so really fast and really strong shear. We know that if you have a polymer solution, when you shear so fast, you get shear thinning behavior. But near the body is bulky. The body rotates only at 20 hertz to balance the torque. So body doesn't feel that much of shear thinning. The idea here is that near this 1 micron size bacteria, you have a 2 type of fluid. Near the flagella, you have low viscosity fluid. Near the body, you have normal viscosity fluid. So they build up this what they call 2 fluid model. By adjusting the parameter of the viscosity or shear thinning, degree of shear thinning, you could have some speed enhancement. So there's some work there. Next one is related to this, similar to this. The idea is that when you have flagella rotating 120 hertz over the length scale of 20 nanometer, you will stretch out the polymer coil. When you stretch out the polymer coil near the flagella, you get no more stress difference. This is like classical rod clamping, right? If you have a polymer, you rotate the rod, the polymer solution clamp up. So no more stress difference will give you a speed enhancement. The last one, published by Wilson Pong in Edinburgh 10 years back. This is the most ironic explanation of what happens. So Wilson did is he bought, first of all, the PVP from Dow Chemical, the same company, although 70 years later. And he dialyzes his polymer. He removed the small molecular weight contamination in the system. And he found that speed enhancement goes away, or at least reduce a lot. And then he claimed that the reason why bacteria swim faster is because they can eat the small molecular weight contamination. They get more energy to swim faster. So all the physics is not there, right? This is the explanation. They published a PNAS paper about 10 years back. Okay, this is all the major theory in the field. And people really fed with each other trying to say, I'm right, you're wrong. So when I get into there, that's around the time that I should go for promotion for my full professorship. And I really don't want to get into the fight because I need those people to write me later. So I say, okay, let's do something different, right? Let's do something different and simpler. That's what I can handle. Let's just study how bacteria swim in colloid, which is a hard sphere particle. See how the hard sphere particle interact with bacteria swimming, okay? Experiments very easy to do. It's like a super easy experiment. You just get some microfluid channel, you put your colloid particle, we vary the size of colloid from 100 nanometer up to 1 micron. We increasing concentration of the particle volume fraction from 0 up to 20%. Above that, imaging is difficult. And 1 micron is limited by sedimentation. If I go too big particle, they all sediment. And then I just mix my wild type bacteria, E. coli, and I look how they swim. So here's the result. The first one I show you here is when I have a 100 nanometer polystyrene particle. So this is really the size ratio, the real size ratio between bacteria and particle. And I increase in volume fraction, I plot in swimming speed, normalized by swimming speed in water. So you can see that there's about very small amount of speed enhancement, about 5% speed enhancement at very low concentration of colloid, about 1%. And then when you add a lot of colloid, it just speed just goes down. Now, if I increase into 400 nanometer, in this case, PMA particle, I see about 50% enhancement at a volume fraction about 4%, and then start to decrease. The largest particle we use is 1 micron PS particle. Now I see a huge enhancement. I see about 80% enhancement. Again, at a volume fraction about 4%, and then start to decrease. Okay, 80% is a lot. I always like to put this in a human scale. This is my student doing the experiment, Xiang. He's a good runner, but this is his speed and the difference of his speed and world champion in marathon. Okay, that's how much we're talking about, 80% difference. Very clear effect. So if I summarize what I show you there, if I just get a maximal speed enhancement as function of the size of the colloid, I see the larger the colloid, the stronger enhancement I have. When I go to really large colloid, I see about 80% enhancement. What's interesting is then plotting this with the result people already know from polymer. So I look all the literature, find out the result where they use relative narrow molecular weight distribution polymer. So you can have a quite good definition of hydrodynamic radius of polymer coil. When you're plotting the polymer result on top of our colloid result, they actually overlap really well. Larger the coil, the stronger speed enhancement. But this is not the only similarity. Another similarity is very interesting, which is the velocity enhancements that anti-correlated with wobble angle. This actually is intuitively easy to understand. If I wobble a lot, I'm rotating a lot, I do not go forward too much. My speed will be small. If I do not wobble a lot, I just swim in a straight line, then my speed will be higher. So there should be an anti-correlation. If I plotting velocity as function of wobble angle, as I tell you, I see almost a linear anti-correlation here. But what's interesting is plotting this colloid result with the polymer result. Again, the color is from literature for polymer coil. Again, I get a very good anti-correlation between the two. So try to submit a paper. The reviewer saying that this is just a coincidence. It's only two things. It's not enough. So then we have to do more. So we then look into the literature to address the reviewer's question. So if you look at the trajectory of bacteria in water, it's a short and zigzag. But if you put a colloid in, you see the trajectory become longer and smooth. And same thing happens for polymer. This is the polymer result from scientific report. In water, zigzag, short, but in polymer solutions, long. These two should be exactly the same. The reason why their trajectory is a little bit longer is because they do experiment in the confined thin film. We do experiment in the bulk. That's why it's slightly different, but I think the general trends are very clear. And out of this, we can extract all the parameters like the rotation diffusivity, runtime, tumble time, as what I mentioned at the beginning of my talk. So this is what we found in our dilute colloid suspension, and this is what they found in dilute polymer solution. There are a lot of data here. I don't need to go into detail. The bottom line is that they all quantitatively similar. Okay, so this is what we say. Well, what do we see? All the 7 reported swimming features are quantitatively similar in dilute colloid suspension and in dilute polymer solutions. This makes us to go to a conclusion here. There must be some common underlying mechanism that determine speed enhancement in both complex fluid. Okay, no mathematical proof yet. This is purely experimental observation. So if you believe this conclusion, now let's use our result to testify all the existing theory in the field. Just remind you, we see more than 80% speed enhancement for volume fraction less than 4%, very small amount of colloid. So let's use that to test the first theory. Of course, this is not right, because at 4% volume fraction, particles don't even touch each other. They are really far away from each other. There's no way that a particle form any gel network in the system. So this cannot be right. Shear thinning. At a full weight volume fraction percent, Einstein formula for viscosity of suspension works, right? You're not talking about very dense suspension. So you just use Einstein relation. You see that viscosity of suspension is about 10% higher than water. Let's say you shear thinning so much, you completely get rid of this actual viscosity. You essentially shear in water. That's still far from enough using any of the 2 fluid model to explain the 80% speed enhancement. Those two fluid models cannot be right at so low concentration of colloid. We use hard particles, polystyrene PMA. The modulus is 2 to 4 gigapascal. There's no way that any bacteria will deform the particle, give you normal stress difference. Lastly, whether bacteria can eat those particles. I was naive enough. I worried that E. coli may eat the polystyrene PMA. I talked to my colleague in polymer. I say, oh, can they eat that? And my colleague just saying that, Xiang, if they can eat PS PMA, we don't have a plastic pollution problem in the ocean lake anymore right now. So clearly they're not the reason why they swim faster. So we're basically saying that all the theory is wrong if we believe there's some common origin between the two. Now I destroy all the theory, I need to tell you why that happens, right? So this is an alternative way to explain what happens. So the idea is actually pretty simple. Assuming you have a particle, you drag a particle with some force horizontally, of course the particle will move in that direction. At low Reynolds number, this is a famous Stokes law, 6 pi eta A times velocity give you the force. Now suppose that you have this particle near an immobile wall. What happens is that to satisfy no slip boundary condition between the particle and the wall, even though I push particle horizontally, particle has to rotate. People call this rotation, and the way to get the rotation as a boundary-induced torque. There's no real torque. It's simply because the particle moves next to a wall to satisfy no slip boundary condition, particle has to rotate. Now, same phenomenon will happen when you have bacteria swim next to a particle. Bacteria can get very close to particle. Some studies show that the distance can go down to 50 nanometers, really narrow gap between bacteria body and the particle. When that happens, body will feel extra torque toward the solid surface. We call that torque tau B. We can calculate this tau B because the distance is small. We can essentially use a lubrication approximation to calculate how much is torque. So the important thing is this is gamma here, which is size ratio between particle over bacteria body, and the logarithmic dependence because it's lubrication approximation. So this torque has to be balanced by something because all the micro swimmer, when they swim, it has to be force-free and torque-free. What balance this? We argue that it's balanced by the twist angle between flagella and body. Remember, when the flagella bundle form, it always forms some angle with the body. And if you feel extra torque, the body and flagella will align better. So we're assuming that the hook, which links the flagella bundle to the body, is a linear spring. So we have some equilibrium angle is original state, and because there's extra torque, it will bend to a new angle theta. And K here is essentially the bending stiffness of the hook. So if we just link those two, saying that torque-free condition, this two has to be same, we can actually we can predict how the velocity change with the size of ratio. Here we just use the empirical relation that we got from experiment, how the velocity change with angle, because we know how angle change. I hope this works. Yeah, we know how the angle change. We just link angle to velocity. This will give us a relation between velocity and size of the particles. There's only one fitting parameter, which is the K, the bending stiffness. If we fit our data, we got a very good fit, and the fitting give us K on order of 7 times 10 to negative 19 Newton meter. And Hauerberg actually did some measurement using optic tweezers, bending the flagella and the body. They found the bending stiffness should be on order of 5 times 10 to negative 19. So it's really the same order of magnitude. Okay, so this showing that our theory actually worked well. Why does it work for polymer coil? Because we know that if you put a polymer coil in water, most likely water cannot go into the center of the coil. This is actually the non-draining case called Zim model. So water, when shear around the coil, will shear around the coil and will give you no slip boundary condition at outside of the coil, which give you the hydrodynamic radius of coil. That's why when bacteria swim next to a coil, it's same as a swimming next to a hard sphere particle. Okay. So the last thing is, of course, right now we are using empirical relation between velocity and theta from experiment, but actually we can also predict this relation. I will go quick here because this is not the important part of that. The idea is actually a high school type of a calculation, although mathematically it's a little bit tedious. So essentially you have your body rotating with some velocity, flagella rotating with some velocity, because the torque has to balance. In order to balance torque, the whole thing has to rotate together. That will give you the center mass rotation. And everything's linear in this limit, Stokes law. And then if you just balance the torque and balance the force, you can predict how the wobble angle relate to the swimming speed of bacteria. So I skip that. So you can actually have a pretty good relation. If you just insert that relation back to your theory, you can get everything fit without any fitting parameters. Okay, let me conclude this part of our result. So someone read a news article for us. Actually, this is everything I want to talk about for this story. So if you have bacteria far away from particle, they wobble a lot, they swim slow. When they're getting close to the particle here, they wobble less, they swim more straight, they get higher speed. Now, before they can recover their original wobble behavior, if you encounter another particle here, they will keep has reduced wobble, and they will have on average higher speed in swimming. So that's essentially the idea that I want to show you here. Okay, so that's also explain qualitatively how the swimming speed enhancement depends on volume fraction of particle. We do some back envelope calculation. The volume fraction where we see maximal speed actually consistent with this picture that bacteria need to constantly reduce the wobble when they're swimming in a suspension of colloid. Okay, so that's the first part of my talk. As I said, I want to tell you a story, both of bacteria and also algae. Algae is a more complicated organism, but this is again a very it's the model organism people use a lot. Yes.
Just before you go into the algae.
Yep.
So does this explain then? You also saw a drop in the speed at as the volume fraction increased, and do you see a drop in the speed as the radius of the particle increases? Like, is there any secondary effect that we're missing in this story, or can you just keep increasing?
If I understand your question right, yes. If you go to higher and higher volume fraction, eventually there will be another effect, meaning because when they swim, they will hit the particle. When they have so many obstacles in their swimming, then their speed goes down. That's what happens after you reach the peak, you start to go down, right? You have to have some competing factor, otherwise you won't be able to see the non-monotonic trend. You get some trend that give you a higher speed, but some trend that give you lower speed, and then together just give you the peak. We haven't worked on the higher concentration part yet, but that's a good question. Okay, so let me move to this algae one. So how do algae move? Algae move by beating two filament flagella in this breaststroke type of motion. Of course, this is a low enough Reynolds number. When it's even they do breaststroke swimming, they're actually going back and forth, right? So if I'm beating, I go forward. If I retract, I have to go back a little bit, although I didn't go back that much. But then if I'm beating more, I go forward further. So they're actually doing this. Not like human, when we do breaststroke, we always go forward. We never go backward. This is a very good model system for many different things. Flagella propulsion, cilia dynamics, which is very important because actually the structure of the cilia or the flagella here is essentially the same as what we have in our body. Almost every organ in our body has some filament to move fluid around, like mucus in our lungs, essentially the same structure. That's why this is very good organism to study the dynamics and structure of cilia dynamics and study hydrodynamic interactions, synchronization, many different things, okay? But the important thing is that Reynolds number is still small. If I'm thinking about average swimming speed of the algae, this gives you Reynolds number 10 to negative 3. If you're thinking about the beating flagella, which is faster, you get something on the order of 10 to negative 2. Actually, 5 times 10 to negative 3, about 10 to negative 2. So that's why the swimmers always think as a model for low Reynolds number motility. If you look at the textbook, they're always talking about the swimmer and try to understand the swimmer. Someone mapped the 2D flow field around the swimmer. So this is a time average flow field over one beating cycle. And this is a flow field within one cycle at different phase. You see different shape of flagella. This is a flow field. This is a very hard experiment to mapping the flow field at the scale of microns and to see how the flow moving around when the flagella of the algae moving. So consistent with the low Reynolds number idea, you can actually quantitatively understand the flow field by using what they call Stokes-Lit model. For those of you who do not know Stokes-Lit is really a fundamental solution of a Stokes equation. You just have your Stokes equation, you add the point force, singular point force, and the solution for that is one Stokes-Lit. So you put 3 Stokes-Lit at location of the body and location of 2 flagella. You just approximate 2 flagella as 2 Stokes-Lit. You approximate body as 1 Stokes-Lit. The sum of the 3 has to be 0 because of force-free condition. And when you have that, you can actually quantitatively predict the flow field. The line here is a prediction of this 3 Stokes-Lit model. The simple is from the experimental measurement of the flow field. So we read this paper, and then I immediately tell my student, okay, this is a 2D flow field. Is there any way we can map out the 3D flow field? Because apparently the flagella beating this way is not cylindrical symmetric. The 3D flow field will be different. Can we do that? My students say, you're crazy. This is so hard experiment. You just do 2D. How can you do 3D? So I start to give this into undergrad students because they usually just accept whatever you say, right? So I give it to them, try it out. So we start to try it out, okay? So the goal, which I'm going to show you, if I don't get that, I won't have this talk here, is I'm going to show you the 3D flow field around this micro swimmer, which reveals something that's very, very interesting. So how we do that? We use holography. So holography is a very simple imaging technique. Essentially what you have is that you have a collimated laser light coming in, the laser light hitting a particle, the particle will scatter light. The scatter light interference with the incoming light, you start to see the diffraction patterns. When you look in the diffraction pattern, this is one of the hologram we see. When you see the diffraction patterns, the center of the diffraction pattern tells you the XY location of the particle. If you calculate the ring shape, you can actually get Z location, how far away this particle away from the focus plane. Then you get 3D location of that particle. For this picture here, actually we see 4 particles. If you do the reconstruction hologram, you can reconstruct the position of particle in XY, XZ, and ZY plane, okay? And then if you just measure the Brownian diffusion, it gives you perfect Brownian diffusion, which will tell you the resolution of your image. So we're applying this to algae flow. So this is some of the hologram we see. You can see a 1 green algae swim by. When swim by, we'll push particle around. All the rings that we can reconstruct to get a 3D location of both algae and the particle. And this is a closer view of algae interact with the particles. Okay, so let me tell you what we got. This is a time average flow field. By the way, none of this is published, right? So this is really a new result we got. We're writing up a manuscript. So this is a time average 3D flow field. This is a flow field in 2D, XY. This is a flow field you see in YZ. This flow field you see in XZ. In 2D, in XY direction, we see the same thing people see before. Mainly you have stagnation point in front of algae and 2 side vertex on the side of algae. If I go back to what I showed you early on, this is essentially the same as what they see there, right? Stagnation point and 2 side vertex. But what's more interesting is that if you look the another plane, you start to see there's a hairpin flow structure in front of algae in XZ direction, and then the core of the vertex serves as a source, flow source, pumping fluid in Z direction. If you compare this with the 3-Stokes-Lit prediction, essentially it's very similar. Again, 3-Stokes-Lit model works really well. You get a source at the core of the vertex. You also have hairpin structure in front of algae. We can extend that further, but just a small extension, you can put a real size of sphere there, then you get a little bit better representation of the flow. But what's really interesting is look at the time result flow. This is a time average flow over 1 beating cycle. If you look the flow over 1 cycle, you see something very interesting. Before I show you what happens, let me tell you what the 3-Stokes-Lit model predict. This is a prediction of the 3-Stokes-Lit model. Essentially what you have here, you just have your 3-Stokes-Lit, you oscillate the magnitude of the force back and forth sinusoidally. And then you see the flow field. The flow field essentially streamlines, stay same. Only the flow direction flip back and forth. When you're moving from the power stroke to recovery stroke, flow just flip. Nothing else happens over 1 cycle. And here's what we see experimentally. It's way more complicated than that. Okay, so for untrained eyes, you may just see noise happens here, but let me point out 2 features. First feature is that if you look behind the algae, you can see the flow actually is rotating counterclockwise. This is different from the prediction there. Their flow just a flip back and forth. Here, the flow really rotating. The second thing is that you start to see vertex forming in this flow. There's 3 vertex. 1 vertex happens in the power stroke, rotating counterclockwise, first forming here, and then translate back in this way. The second vertex in the recover stroke is mainly stay there, but rotating clockwise. The third one is in front of algae in the recover stroke, rotating counterclockwise, first forming here, and then translate in that direction. That's the features that we see here. None of this you can explain by Stokes model. Then what happens? So it's actually, there's some inertia there. Even though everyone thinks this is a low Reynolds number flow, everyone using this as a model for low Reynolds number motility, there's some effect of inertia in this system, in this tiny swimmer system. So what I'm showing here is a calculation of 3 oscillate. Oscillate is a fundamental solution of the unstudied Stokes equation. Stokes equation is without this term. Now we're adding this time derivative term, this acceleration, which gave you the fundamental, again, point force, sinusoidally oscillating, which gave you 1 oscillate. We put 3 oscillate at two at location of flagella, 1 at location body. Now you can see mainly all the features that you see there. You see the flow rotating, and then you see a vortex forming and shedding backward. Okay. So it's not surprising that low Reynolds number flow will break down at a certain limit, because low Reynolds number predict that if I'm moving one flagella, no matter how far you're away, you'll feel the flow immediately. Of course, that's wrong from physics point of view. But the important thing is that close enough to the algae, you should see the low Reynolds number effect, because viscosity is so strong, when I move, the approximation that flow will follow it is very good approximation. So the important thing to know here is that the length scale where you expect the low Reynolds number works is this scale on order of 140 micron. But from our experiment, we see that on order of 10 micron, you already see the effect of inertia. So inertia show up as something that's so close to the algae, that's completely different from the expectation from theory. Now the question is that why that happens. So to answer that question, we run some simulations using immersed boundary simulation. We simulate essentially the full Navier-Stokes equation, including both the unstudied acceleration term as well as the nonlinear convection term. And this is a flow field in XY, flow field in XZ. The good thing for simulation is the flow field is so smooth that we can do higher order derivative. Then we can directly compare the ratio of the inertial force over the viscous force. If low Reynolds number prediction is right, the bottom term should be much higher than the top term. But if you look over one beating cycle, there's some region that's become very right. We call those the inertial hotspot. So when it's right, this log scale is become bigger than 1 or 10. So the inertial force is same order magnitude as the viscous force or 10 times higher than that. So where does the inertial hotspot come from? If you look in the inertia, this is basically the snapshot of that picture. I highlight the inertial hotspot here, here, and here. This is so close to the body. The inertial force is so strong. It's 10 times higher than viscous force. Why that happens? So if we look at the inertial force itself, we do not see any of the hotspot. Okay, at those locations where you see hotspot, we do not see anything. At this location of hotspot, we don't really see hotspot, and this part we don't see hotspot either. But if you look at the viscous force at location where you have very strong ratio, actually have a cold spot, those regions become blue. Those regions become blue. Again, if I just take a snapshot, which give you a better view here, this one here, whenever we see hotspot, which I highlight with dash circle, I see the location where I see cold spot in viscous force. Same here. So the inertial hotspot is not because inertial force is high. It's because viscous force is low. Why that's the case? Now you look carefully of the streamline where you see this low viscous force. Those is the location where you have an inflection point. So very clear here. You see the flow changing from this curvature to that curvature. That's the point where you have inflection. The inflection point in this XA plane, because in Y plane it has to be either maximal or minimal because the symmetry of the flow is actually a monkey saddle of the flow. So essentially at the location of the monkey saddle, you have very low viscous force, which make the inertial force, relatively speaking, much higher. Let's give you the inertia effect in the system. And I just want to quickly comment that the nonlinear term is always small. So if I look at the nonlinear term, which is infamously give you all the turbulence behavior, this term is always low. It's always on order of 10 to the -2 or 10 to the -3. So the inertia, the nonlinear term is not important, meaning that you don't have steady streaming in the problem. Time average flow will not reflect any of the inertia effect. That's explain why the Stokes can predict the time average flow well, because nonlinear term does not mix different harmonic mode in the flow. So why we should care about that? How the inertia give you any function significance in algae flow? First of all, if you calculate swimming efficiency, which is the efficiency you compare the energy you need to drag the body at the speed of swimming versus the mechanical power you put into the fluid, we found that with the inertia, your swimming efficiency goes down. So the swimming efficiency with inertia is about 6% lower than swimming efficiency without inertia. So algae pay more to swim in this case when you have finite inertia. But it gains something. It gains the fitting efficiency. Fitting efficiency means that when I'm beating flow, how much more flow I can bring closer to my body. The more flow I bring into my body, potentially I can get more nutrients from the nearby environment. When I calculate the fitting efficiency, the fitting efficiency gain by 9%. So you gain some fitting efficiency by losing some swimming efficiency. Well, what's more interesting is thinking about this inertial vertex shedding at this so low Reynolds number. So vertex shedding is a very important topic for locomotion of animals. So if you look at the literature of insect flagging bees, Cornell, Jane Wang, she studied a lot of that. Also fish. When fish beating the tail, it generates a lot of vertex, shedding a lot of vertex. This is a simulation by Jane where he simulated the insect fruit fly wing. So you have an insect wing, the fruit fly wing, the wing beating this way and shedding vertex. When the vertex shedding away, you carry out the momentum and you get repulsive force, which make you hover in air. So this is actually play a big role in higher Reynolds number regime. No one think that you will get vertex shedding at low Reynolds number, but we found that you could have vertex shedding, inertial vertex shedding at low Reynolds number as low as 10 to -2, -3. We believe this is really the smallest organism people know that's shedding inertial vertex in this field. What's the broader consequence? So people study, as I mentioned, using algae as a model for study flagella and cilia dynamics. Almost all the simulation and theory on flagella cilia dynamics always treat everything as low Reynolds number flow without inertia. So hopefully our study can convince people that when you do simulation on this more complicated system, you should thinking about inertia effect, even at a very low close distance away from the beating flagella. So with that, I'd like to conclude my talk. First part of my talk, I tell you how flagella, the bacteria swim faster in complex fluid. And the next one, I tell you our research to map the 3D flow field of green algae. So this is really the beginning, right? So once we have this method, now we actually applying this method to mapping 3D flow field of many different swimmers. It's still very hard experiment. Eventually, I got really a whole army of undergrad students, plus one postdoc, 2 graduate students working on this project, because it's extremely hard to really accumulate large enough data to get 3D flow field. But our 3D flow measurements show you there's actually unexpected inertial effect, even in the model system of Reynolds number swimming. And we show that inertia coming from the saddle point of the flow, and we discuss the functional significance of algae and flagella dynamics. With that, thanks for your attention.
Thanks very much. Do we have questions from the audience? Looks like.
Thank you. It's really fascinating talk. Since you are talking about results that are not published, I think I will ask you a non-traditional question, which is why go to 3D, right? One answer could be, oh, I mean, it's something that should be done, and it will be technically difficult, so there is an achievement in there. Or did you actually suspect that there was something going on and that inertia actually was going to have? Did you already have kind of an inkling of what was going on in there or not?
I don't have idea that the inertia is important, because everyone thinks that this type of swimmer, you should use a Stokes law, low Reynolds number hydrodynamics should explain everything. The reason why we go 3D, as I said, is mainly because the beating pattern is not cylindrical symmetric. You're beating in the plane. You do not beating out of plane. So if you're looking the flow back in the out of plane direction, you should see maybe you should see some interesting flow structures. That's our motivation at the beginning, why we want to get 3D flow field around swimmer.
So if I understand correctly, your explanation is that you are expecting something interesting to be there.
Yeah, we're expecting some very interesting flow structure out of the plane. So we want to see those out-of-plane structures. And the another thing that maybe also driven us to go there, because if you look at the 2D flow field, like I show you here, I don't have the data here to show you, but in the manuscript, we start to have it. In the 2D flow field, you see this vertex, right? Question is how those vertices connect in 3D. Are they connecting like a smoke ring, that you have this vertex like donuts, that a torus connecting them together, or they sort of diverge? So this is sort of a question we trying to look into, because in 2D, you only see two vertices, but in 3D, they must connect in a certain way. What's the topological structure of this vertex ring in 3 dimensions? That's something that actually we have data, very complicated. During one cycle, the ring form and deform and then disappear. So very interesting result there.
I've got a question. So this actually connects to your answer to Luis's question. The z-axis symmetry is even in your model. So I guess it's part of it is biology. Is it known that there is kind of symmetry in the stroke, or do the flagella actually move outside of the XY plane?
Very good question.
And then in your models, do you impose the symmetry or not?
Yeah. So most of study, they treating flagella beating in XY plane, but there's some studies show that they're actually beating out of plane. Over one cycle, they're beating like a figure 8 sort of shape, very small out of plane beating. There's some experimental work, they holding the algae with a pipette and they looking from front. We, in IB simulation, immersed boundary simulation, we did add out of plane beating. This gave you some first order correction of the flow structure. But all the flow structure I'm showing here, they stay there. Qualitatively, they are there, but quantitatively, there's some small modification of what happens. They dominantly beating in XY plane, they're small out of plane beating.
Thanks.
Thank you. So at the first part of your talk, you described how the swimmers can go faster in a colloid suspension, right? So maybe this is a long shot, but do you think there's any chance you could cultivate an environment of bacteria with like a sparse colloid suspension, so not many particles, where there's a competitive advantage, and then over many generations with these bacteria or swimmers seek out particles, and you could observe that maybe a long shot, but
it could. We restrict to writing that in our paper because, first of all, we are not biologists, and biology doesn't like that we claim some evolutional advantage of the thing. But is the swimming enhancement just coincident, or is something that bacteria evolved because in their environment they have all different particles and proteins and DNAs? We don't know that. Again, I'm not a biologist. I cannot answer that question. It could be the way that they're forming this multiflagella and then forming angle is because they want a speed enhancement in their natural habitat where you already have particles. So it's not like we have to do that in lab to select the species. They already have that because, again, in their natural habitat, they have food full of different type of particles in their environment.
thank you.
Right.
I'll throw in actually a quick follow-up to that question. In your cartoon, in the first part of the talk of this speed up effect due to the proximity of the particle, you don't, I guess my naive intuition would have been that, yes, when you get this, this boundary layer effect, this torque due to the boundary layer, my intuition wouldn't have been that the overall motion is still straight, but that it would actually cause a curvature in the path of the bacterium so that you would see arcs of circles or something when they pass the particles. Is there a reason that doesn't happen, or does it happen when it averages out?
Yep. So I will answer your question in two parts. The first part is directly address your question. The second part is add on top of that, which you may not ask, but I think it's an interesting point to point out. If the particle is large enough, yes, you will see that. Actually, someone do this research. They're seeing big circles. If you have a bacteria, especially E. coli, when they get in surface, they were trapped by the sphere, and they were swimming along the sphere. And people know that because if you have a complete flat wall, when bacteria get to the wall, they were trapped in the wall because the image image force on the other side of the boundary, you will get some trapping effect. But what we were talking about here, the particle really on the same size of the body, right? It's really very small surface area. So that's probably directly address the question that you have. The second part of that is actually very interesting. Most of the time, actually, most part of the project we are thinking to how to explain that is you must have some symmetry breaking mechanism, because if you want to have a better alignment, you must have the particle on one side of the bacteria. If you have a particle on the other side of the bacteria, actually you bend more. You will get more wobble than less wobble. And if you just put a particle randomly in a suspension, you just have your particle, bacteria swim in a random array of particles, you will see similar probability of enhanced wobble than reduced wobble. Why the reduced wobble effect show up? You must have some symmetry breaking mechanism. The way the bacteria break the symmetry is actually long range flow. So the calculation we have here is a lubrication calculation. It's really when they're getting very close. But the calculation has basically putting bacteria and particle there by hand and saying that you located at those locations, let's calculate how much torque you feel. But in reality, before the bacteria getting close to the particle, it's actually already interact with the particle through hydrodynamic interactions. Bacteria, as the 3D flow field for algae show, they actually generate a long-range flow around them when they swim. So this long-range flow actually breaks the symmetry. The reason why that happens is that we know bacteria is like a pusher flow. So pusher means that they will generate flow in front, pushing fluid back, and then bring the flow back into the waste. So basically the direction flow is pushing out in the head, pushing back in the tail, and the flow coming in the waste here. So this flow essentially will push all the particle away from their helical trajectory and bring particle to the waistline. So this is the way that they break the symmetry. So essentially, you have a much higher probability to see particle outside your trajectory, very few chance to see particle within this helix. Only when you are in the helix, you will enhance your wobble. But if you're outside the helix, you always reduce your wobble. And the more you swim straight, meaning that this helix gets smaller and smaller, this effect go away. So even you swim just straight line, there's no difference between inside and outside, and this effect goes away. That's why you can only get maximal speed enhancement when you swim straight. You cannot get more than that because this effect gets weaker and weaker when you swim more and more, less and less wobble. So that's a long answer for that. I didn't have time to talk about it.
Really interesting. Thank you for the super interesting talk. Let's